Good morning. Thanks for joining Intertech this morning and our Maximizing System Efficiencies for Commercial Geothermal Systems interactive webinar. Go ahead next. This morning, we have Jeff Hammond from Geo-Flo as the presenter for the webinar, and my name is Brian Erlob. I'm the Commercial Sales Manager with Intertech. And today we're going to be talking about maximizing system efficiencies for commercial geothermal systems. With that presentation, we're going to be talking about the EER versus system EER, the ASHRAE 90.1 pumping watts, ECM versus VFD technologies, system types, and some example pumping retrofits. And at the end, we'll have question and answers. And some upcoming webinars that we're looking forward to. Obviously today, again, maximizing system efficiencies for commercial geothermal systems. And Thursday, January 19th, we have scheduled the White Rogers Sensi with Wi-Fi, thermostat, and applications. So to get the most out of this webinar today, first of all, please take notes and hold your questions until the end. That would be great. And we could submit those questions either through the question bar on your right, okay, or we can also, I'm sorry, yes, just add your questions to the question bar, type those in, and then we'll go ahead and answer those. So with that, let's begin.
All right, thank you, Brian. This is Jeff Hammond with Geo-Flo. I appreciate the opportunity, and thank you everyone for joining our webinar this morning. We're going to talk about commercial pumping. We have some opportunities now that we didn't have even just a few years ago because of some of the new technologies. So that's what I want to concentrate on. You saw the topics that Brian covered, lots of acronyms and abbreviations, so we'll try to clear all those up as well. We're going to start off with AHRI efficiencies. AHRI, of course, is the Air Conditioning, Heating, and Refrigeration Institute, and it's sort of the gold standard for efficiencies to make sure that all the manufacturers are testing to the same standard. So when you're comparing one brand to another brand, you know that the testing is done the same way. And I have an example here of one of the Intertech commercial units. This is actually a very efficient unit, especially for the size of the cabinet. You can see here in the table, the full load EER is 20.1. So that's really good for a commercial unit. And that number includes the pump penalty correction as well as the airside static pressure correction. So AHRI wants everybody to be on the same page as far as how things are tested. And so what they do is they look at the pressure drop of the coaxial heat exchanger or braze plate heat exchanger, and that includes a pump watt correction. So based on that pressure drop, then additional watts are added to lower the EER. On the same token, the air side is corrected to zero static pressure. So that way we can't have different testing occurring based upon the ductwork that's attached to that heat pump if it happens to be a water-to-air heat pump. So those two corrections, the pump penalty correction and the air side static pressure correction, are rolled into this EER number, and that helps with making sure that everybody's testing in the same way. We're getting some background noise. Make sure everybody is muted here before I move on. Okay, great. So when we talk about the pumping contribution to the AHRI efficiency, that pump watt penalty that I mentioned in the previous slide, this is how it's calculated. We just simply take the flow rate and the pressure drop of the heat exchanger, and we calculate the pump power correction based upon those numbers. So in this example, that 4-ton VS unit has a pump power correction of 79 watts. Now that may or may not be the actual watts, but that's the number that's used to generate the EER. So the heat pump watts plus the pump power correction watts are rolled up into that EER. And so that number in the AHRI data includes the pump watts, but the catalog data does not include the pump watts. And we'll need to look at the catalog data to get our system EER. System EER would be the heat pump plus those external energy use like the pumps and so forth. And it can be pretty significant, so we really have to watch pumping on a commercial job, especially to make sure that we're not putting in a very efficient heat pump and actually ending up with a low system efficiency. So AHRI, as I mentioned earlier, sets the standards. It's a great way to make sure everybody's on the same page, testing in the same way. So we have the pump penalty and the airside correction, as I mentioned. And now we can compare the EER with one brand to the EER and another brand, and we know that they've been tested in the same manner. But it really doesn't tell us what the system efficiency is. So we can have the best heat pump, as I mentioned earlier, that has a pretty low system efficiency if we're not careful. So we do have to look at the actual system efficiency. EERs and AHRI are really helpful and necessary, but we do want to look at the whole job, especially on a commercial job with multiple heat pumps. So system efficiency is the heat pump energy usage, which is going to be our compressor, fan, controls, and then external energy usage, and that's primarily the pump. There could be some additional external devices, but for the most part, it's going to be the heat pump and pumping. And we want to try to use, as at least a guideline, ASHRAE 90.1. 90.1 is a standard for commercial buildings, and it's really a minimum. So if we design to ASHRAE 90.1, that's the lowest efficiency we want to look at, but we might have higher efficiencies if it's a lead building or we have other goals. 90.1 should really be our lowest. You'll find state and provincial or even local codes will use a version of 90.1 in many cases. So that's our minimum level, and we should always try to exceed 90.1 from an efficiency standpoint. Let's take a look at the catalog data. The catalog data is just the heat pump, does not include that pump penalty. So when you look at the column here, and this is that same commercial unit, the VSO48 4-ton commercial unit, the power column gives us the power of the compressor and fan and controls. So in this case, at 80 degree entering water temperature, 12 gallons per minute, 1610 CFM, we're using 2.83 kilowatts. So that's the power of the heat pump only. It does not include the pumping watts. The EER column is just simply the total capacity divided by the watts. So we have 53,100 BTUs per hour divided by 2.83 kilowatts. That gives us 18.8 EER. And that EER, again, is just the heat pump. The AHRI EER, because it's corrected for the air side and the pump penalty, and because it's at 77 degrees instead of 80, 80 is the closest I could get with the catalog data without interpolating. The AHRI EER then 20.1 rolls this number at 77 degrees into the pump penalty and the air side correction to get that 20.1. So these are good numbers to look at when we're designing a job. The system EER then, if we calculate that, we're going to use the heat pump watts, 2830 or 2.83 kilowatts, and then we have to add in a pump. I'm using just a standard little 2699 Grundfos circulator. It's a wet rotor circulator, cooled and lubricated by the fluid going through it. And it's typically about 180 watts when we're looking at 12 gallons per minute. So if I add in the 180 watts to this formula, the total capacity divided by watts, I have my capacity of the heat pump divided by the watts for the heat pump and the pump watts. So now my new EER is 17.6, which is the system EER if I were to have one 4-ton heat pump and one little circulator. Now, we'll see later on that we have to be really careful of choosing pumps because this one actually doesn't even meet our 90.1 super high efficiency rating. If we use two pumps on this system, then we have about 360 watts, and our system EER is 16.6, capacity divided by total watts, heat pump plus the pumps. So it just kind of gives you an idea of how those calculations work and how important the pump sizing is. The 90.1 standard also requires variable speed pumping for over 5 horsepower pumping systems, and so that's important on commercial jobs. But really, we want to look at variable speed on any commercial job, even if it's under 5 horsepower, just because of our efficiencies. The pumping budget then is 22 watts per gallon per minute. So that's what we want to shoot for to hit 90.1. Again, that's a minimum efficiency. So if we can get better than 90.1, we're in better shape for the end user, for the customer. So if we look at our example earlier, 4-ton unit, 12 gallons per minute at 22 watts per GPM, then our ASHRAE budget to hit 90.1 is 264 watts. So I misspoke earlier. The one pump would have actually met this. The two pumps would not meet the ASHRAE 90.1 budget. One pump was 180 watts, two pumps was 360 watts. Now, if you look at the pump penalty from our AHRI calculations, it's only 79 watts. So to get AHRI numbers, we really have to be very efficient from a pumping standpoint. I use this manual quite a bit as a benchmark. This is a pretty new manual. I think it came out in 2015. It's the Geothermal Heating and Cooling Design Guide from ASHRAE. Steve Cavanaugh and Kevin Rafferty have had a lot of experience over the years in designing systems. There's a really nice benchmark. It's a table that shows watts per ton, and I've added in watts per GPM so that we can compare to the ASHRAE 90.1 budget. So this is the table. It looks at installed pump power in horsepower, power in watts into the pump motor, and then gives you a rating, which is a grade A through F. I added in the red text here so that we can compare what's in the ASHRAE table to what we talked about with the ASHRAE 90.1 budget. So if we're looking at less than 5 horsepower per 100 tons or less than 45 watts per ton, that converts to our less than 15 watts per GPM based on the ASHRAE budget. If you remember, that was 22 watts per GPM. So that would give us a grade A. If we're at the ASHRAE 90.1 standard of 22 watts per GPM, that's actually a grade B. So it's not the most efficient that we'd want to see in design, but it would meet 90.1, which is required in a lot of cases. One thing to keep in mind when you're looking at all these numbers, whether it's a grade A, grade B, grade C, is the available head that we want to design for as far as efficiencies go. When you look at the very high efficiency applications, you can see here in the table, you want to try to be less than 46 foot of head when you're designing the system. So a pressure drop has to be pretty low to get these numbers. As the pressure drop gets higher, then we're certainly going to use a lot more watts. And that might be a fairly minor change. We might go from, for example, a 3/4 inch pipe to 1 inch pipe to get our pressure drop lower and allow us to go to that smaller size pump, get to this grade A rating, and now all of a sudden we're saving a lot of energy and our system efficiencies are much higher. There's another thing to consider here. When you're in this range, less than 46 foot of head, now you can get into more high efficiency pumps. When we're in the higher head range, we're really stuck with some of the older technology. So all this really ties in to designing the right system. Some of that new technology includes ECM motors, and I'm sure most of you are used to ECM motors, especially if you've used any of the Intertech product with ECM fan motors. It's pretty common now and has been for a long, long time on the fan motor side, but we're starting to see a lot of ECM pumps. And that technology is more efficient than a typical VFD, which would be a separate pump and a box on the wall that's a variable frequency drive. Some of the ECM motors have wireless communication, so we can talk to a backup pump. We can operate in lead lag, primary backup, both pumps at the same time. And those controls are typically built in, so we have some cost savings, a lot less wiring, and a more efficient system. Almost all of them have some capability for building management systems using a network card, and I mentioned they're higher efficiencies. So some of this new technology makes it a lot easier to get to 90.1, but it also makes it even easier to get to that grade A rating, and our system efficiencies improve quite a bit. Here's an example of one of the ECM pumps. The pump head you can see here is the red and the black section, and then the volute is foam insulated in this sheet metal cabinet so we don't get condensation at low temperature operation. So this is essentially the what would be a VFD on a typical pumping system that has a variable speed pump with a separate VFD. This takes the place of that VFD having the controls built into the ECM motor. So there's quite a bit of savings there, both in efficiencies and in installation cost. This is a smaller one here, the 40 series. It would be in the 10 to 20 ton range, but it does have all the built-in controls for differential pressure. We can do delta T control, primary backup of multiple pumps, alternating, and so forth. And I mentioned the building management options. So this is an example of a typical ECM pump for a smaller job. Larger systems, we get into larger pumps, same basic technology. This is our ECM motor, just a larger volute, higher flow rates. In fact, we have some really large pumping systems that would be in the up to 500-600 gallon per minute range with that same style of control, ECM type motors. All the same efficiencies that I had on the previous slide with the smaller pump. When we get into the even higher flow rates, larger systems, we can look at dual head type operation. This one has the same insulated cabinet type that we looked at earlier. This one happens to be a foam insulated, but it's a dual head pump in this picture. So we have one volute with two pump heads, and that gives us the advantage of having only one set of piping connections. But now we can do a primary backup, lead lag, cascade operation, and we're saving a little bit of cost also by having only one volute. So this really makes for a nice system on larger jobs where we need higher flow rates. These pumps operate in parallel, so now we can get double the flow at the same head. To compare, I just used two Grundfos variable speed pumps. The top chart is a 2 horsepower high efficiency vertical inline pump. So this one is a pump with a separate VFD. The bottom is the Magna 3, which is the ECM pump. If you look at the numbers now, at design conditions, we still look pretty good. This was a job with 80 gallons per minute at 40 foot of head. And at full load, we're at 1,225 watts. So that's still pretty good compared to especially an old standard in suction or inline pump that might be constant speed. That's a pretty big savings. We're at 15.3 watts per GPM. So easily we're better than the ASHRAE budget of 22 watts, 30% better in fact. But when we look at the chart, which that's coming up again from the ASHRAE manual, it was 15 watts for grade A. So we're just slightly under that grade A pumping. If we look at the ECM pump, now at full load, we're 990 watts, and we can easily meet, again, ASHRAE 90.1, but we can also meet that grade A rating for pumping with the ECM pump because we're only at 12.4, and we needed to be at 15 to meet that grade A. Now, these ECM pumps are not rated in horsepower, which is the case with most ECM motors, but it's approximately 1.5 horsepower. So even the same flow rates here, 80 gallons a minute, and the same head, 40 foot of head, you can see here if we were to compare just the motor size, it's about half a horsepower less. So that obviously gives us some advantages from a energy usage standpoint. We'll go back to that table, and you can see here the VFD is just over that 15 watts, so it's about a B plus, I guess, when it comes to ratings. And the ECM pump at 12.4 watts per GPM, we're easily under the 15. So we're a solid A for that ECM style pump when we look at system efficiencies. When we compare, I'm just really reiterating what we talked about earlier. We can easily get that 90.1 budget with a VFD or an ECM if it's properly designed. I've seen some VFD systems where they just had way too much head, too much pressure drop in the system, and even a very efficient pump, we're really pushing it to get 90.1. So pressure drop's a pretty big deal on system efficiencies. If we go with the ECM, though, now we're even 18 to 20% less than the best VFD pumps. So this would be an example on the right here of an ECM pumping system, a dual head in this case, built-in controls, and a lot of features that we already need. There are some limitations, though. In this case, we have single phase only. So if we need a three-phase system, the watts are just so low and the amp draw is so low that they aren't even available in three-phase. And we do have some head limitations, and I'll show you that coming up with a chart. But we want to stay in that 40 to 50 foot of head, which again goes right back to that chart. We want to design for that anyway to keep our pumping watts low. But the ECM motor is limited to about 40 to 50 foot of head, depending upon the model. Now, here's a really nice thing that we've found with the ECM pumps. They're a lot less than a pump with a separate VFD. In fact, 30 to 50% less. And so in a lot of cases, you can have a better system, more features, easier to install, and the system is actually less cost, which is never a bad situation when you get better for less. So let's take a look back at that 4-ton heat pump, since it's a good one to compare to. With the VFD, I mentioned we're at 15.3 watts per GPM. ECM's 12.4. So at 12 gallons per minute, we would be 184 watts for the VFD and 149 for the ECM. So easily meets our 90.1 criteria. But if we actually look at that 4-ton unit running by itself on a multi-unit application, the budget here is actually more than what it really runs. And what I'm looking at there is when I have multiple heat pumps, and I have especially if this is a constant pressure application where I have zone valves at each heat pump, when all the zone valves are off except for that one 4-ton heat pump, it's running much less than this 149 watts. It's actually down in the 75 watt range, about half of that. So if I were to go back and recalculate these EERs with the VFD, I end up with 17.1 as a system EER. The ECM bumps me about 0.2 of an EER and typically less installation costs. But if I look at the actual EER when only that 4-ton unit is running, in fact, I can get now my AHRAE EERs. If I were to correct this for the air side static pressure, I would be right at that 20.1. So you can actually tell your customer, if I go this route, ECM pumping, and my pressure drop is such that I can downsize my pumping, I can get those AHRAE EERs, which is even better than what ASHRAE 90.1 requires. And it's a solid grade A in our pumping table in the ASHRAE design manual. This shows you the limitation of the ECM pumps. Our most popular one is this 65-150. It's a nice range for commercial jobs. You can see here about 50 foot of head all the way out to 80 gallons a minute, and still about 45 foot of head even at 100. So if I were to use this in the dual head configuration, I get twice the flow at the same head. So in fact, this combination with two in parallel, I can get 200 gallons per minute at 45 foot of head. Go into the larger size pumps, they're a little bit more limited, about 40 foot of head. So I'm going to have to be in the 140 gallon per minute range with one pump, or about almost 300 gallons per minute, about 100 tons, and I could still use an ECM pump. I could also break this up into primary, secondary, and do some things like that to lower the head even further and get higher flow rates. So in this particular point here, if I can get down to 30 feet of head with this pump, I could get two of them in parallel, 400 gallons per minute, and still stay with ECM technology. So a lot of range here, but you do have to watch your limitation on head. And as I mentioned earlier, these are typically only going to be available in single phase power. So we talked a lot about the pump selection. The system selection is also important. This is a typical central system on a commercial job. I only show 5 heat pumps here, but it would be the same with more than 5. So we have our pumping system here, the VFD block and the pressure differential block. Those are actually built into an ECM style pump in the pump head itself. And in this case, I'm just simply opening and closing motorized ball valves or zone valves. As the heat pump runs, the valve opens, the pump slows or speeds up. As the valve closes, the pump slows down. So I'm always delivering flow based on building capacity, in other words, number of heat pumps running. And as the cost is coming down, it really makes sense to use variable speed even on systems under 5 horsepower, which was our ASHRAE 90.1 requirement. On the ECM pumps like this Magna 3 that we were looking at, it uses a little pressure transducer in the volute, so we're actually measuring pressure, and that communicates back to the controls, allows us to watch those zone valves opening and closing and change RPM based upon the pump. So all that's integrated into the system. If we wanted to try to control pressure drop on larger systems, we can always separate the ground loop from the building loop. In this case, we have a variable speed system with primary secondary, so my hydraulic separator decouples my two pumping systems. This is a low velocity zone, less than 2 feet per second. So now I can have my ground loop in delta T mode. I'm just changing the speed of the pump based upon how much heat is being extracted or rejected to the ground loop. And that's a separate pumping system. So now I only have the pressure drop of the ground loop, which means I can use a smaller pump, most likely an ECM pump, even on a very large job. The building side, I have a little wet rotor circulator for each of these heat pumps. So I only use pump watts with the associated heat pump. If I only have one heat pump running, I'm only using one little pump. So this is a great way to go as well, and getting the pumping efficiencies, pumping watts down, so our system efficiencies are up. The best from an efficiency standpoint, though, is to have variable speed on both sides. So now I have my ground loop pump, which is only sized for the pressure drop of the ground loop. And then my secondary pump here is much like the central system that we had earlier. This is based on differential pressure. So now I have my zone valves at each heat pump, and as the zone valves open and close, the pump speeds up and slows down. So I only have to deal with the pressure drop for the inside building and only the pressure drop for the ground loop, because I have the hydraulic separator decoupling those two pumping systems. So now I can use two very efficient ECM pumps and really reduce my pumping watts. So the system type is just as important as the pump selection, and keeping that pressure drop low is how we're going to attain that. This is what we typically would use on a primary secondary system for the heat pump. This would be the pump that's mounted at the heat pump, and in this case we would only turn on the pump when that heat pump is running. This happens to be a 3-speed pump. You can see the switch here, so I could choose high, medium, or low, and save a few watts there as well if I went with a lower speed. Now, this isn't the most efficient system because we have, we still have a constant speed pump on the heat pump. The most efficient is the picture I had earlier with variable speed on both sides. But you can see here, I can get by with one pump, even up to a 5-ton unit in a lot of cases, depending upon the inside piping. But so I'll be in that 150 to 180 watt range, typically on the heat pump. My main pump can be as low as 40 watts. Up to its maximum pump watts, which may be a couple thousand, depending upon the pump size, maybe as little as 1,000. Just depends on our flow rate through the ground loop. But the nice thing about this being decoupled is if we have some heat pumps in heating, some heat pumps in cooling, essentially that ground loop pump is almost not even running, because we're not rejecting or extracting from the ground loop. We're just moving it around the building, which is really the beauty of that primary secondary type application, and keeps our pump watts low. We could look at a variable speed pump on the heat pump if we want to increase efficiencies and we don't want to go to two variable speed pumps as central type systems. So we could use this is a little Magna Geo variable speed pump that could be used at the heat pump. It's nice for two-stage systems because now we can run at a lower flow rate on part load. One-pipe systems are popular for labor savings. We have still a primary secondary, but this one pump pumps through the building loop and the ground loop. We size this so that we don't actually reduce. It's the same size throughout the building. And then these little small circulators are even smaller than the ones we looked at earlier, because these only have to overcome the pressure drop of the heat exchanger and a small little bit of piping. So these are even less than the wattage that we had earlier. So this would be typically on larger systems. We don't see this much on a 20, 30-ton system, but 100-ton plus, it's fairly common to see one-pipe systems. We have a lot less labor than a two-pipe system. The downside is we can't reduce our piping size as we move through the building. It has to be the same diameter throughout the building loop. So those are just different options for us. Distributed systems are popular in some areas, in schools especially, because they have really some independence. One flow center for one heat pump. So if from a service standpoint and from a using only part of the building, it's helpful in some cases. But this is a pretty high watt system, so we have to be careful of systems like this. We typically have about 180 watts per pump, and because all of these flow centers are in parallel, we have the flow times the number of pumps, or the number of flow centers rather, but we only have the head of one flow center with parallel pumping like this. So we may need 2 pumps in a lot of cases to overcome that head when all of the heat pumps are running. So if we start adding up all the watts, 360 here, 360 here, you can see it doesn't take long before we can pretty easily look at a central system with much, much less watts. So nothing wrong with this system in the right application, but we do have to be careful with not only system watts, but also this parallel pumping application can be a little bit problematic if we're not careful. All right, so I have an example just to kind of put all this into perspective, and this is an actual job where we retrofitted an existing system. It was unfortunately designed with 3 5-horsepower pumps running 24 hours a day on a 56-ton application. So it was just an incredible amount of energy usage, for almost 41,000 kilowatt hours for each pump. And it just didn't make any sense. So we looked at going in with ECM technology, but not only that, we didn't want this thing to run 24 hours a day. So by looking at one dual head pump to replace these 3 5-horsepower constant speed pumps, we can still have redundancy and provide 2.7 GPM per ton, even with just one dual head setup. But the key here is we wanted to add a zone valve to each heat pump so that we allow this pump to speed up and slow down. And if none of the heat pumps are running, it actually turns off. So here's what we're looking at on this example. This is our dual head pump, and I keyed this information into the online calculators. If you go to the Geo-Flo website, geo-flo.com, you can pull up a lot of different sizing calculators. This is one for the Magna 3 pumps. So I found here, once I keyed in my information, then I could plot where that's going to run, and I ended up with that system. So then when we look at wattages, it wasn't really designed for this, so we're not at our A pumping, but we still have 18.4 watts per GPM. ASHRAE's 90.1's budget is 22, so we're still better than the ASHRAE 90.1 budget, even on an originally poorly designed job. We're not quite at the A rating, we're at a B rating, but still we're in good shape. And if all 56 tons is running, we're now only using 2,580 watts. So so that's, you know, a great way to go. This is watts per pump on the left-hand side, but 2,580 is with both pumps running. If 4 of the 6-ton units are running, we're down to 1,400 watts, and if only one of those little 3.5-ton units is running, we're at 100 watts. So now we're just simply cranking up the pump watts based upon the building capacity that's needed. And to compare, that 5-horsepower pump used 3,500 watts 24 hours a day. That's just one pump. There were 3 of them. So you can imagine this was a pretty quick payback. And we could have actually just replaced those pumps with ECM pumps, and we would have been a quarter of the energy usage, even if we let those things run 24 hours a day. But because we put on zone valves, now we're able to determine the flow rate based upon building capacity. So that really helped quite a bit. The lower RPMs and lower horsepower in the building lowered our demand kW. This is a commercial building, so not only did they pay kilowatt hour cost, but they also pay demand costs. So that's a pretty big deal. And in fact, the installation of that dual head ECM pump skid was less cost, significantly less cost, than if we would have replaced like for like. So that was a pretty big deal there. Payback, even if the original pumps were running perfectly well, would have been in months, not in years. So this was hopefully an exception. I hope we don't have a lot of systems out there like this, but this is just an example of the dramatic difference that ECM pumps can make. So just to conclude, we have quite a lot of opportunity here with looking at system efficiencies purely by picking the right pump. And so if we look at the Magna 3 ECM pumps, we can lower the system pumping watts, which increases our system EER. We can operate standalone or with a building management interface. And in fact, we typically use the pump controls even if we do have a BMS card in that pump, because it's already set up for differential pressure. So we might just use the BMS interface for monitoring, looking for, if there might be an error or a fault or something like that. But we, in most cases, just use the pump controls to speed up and slow down the pump. Lower installation cost is never a bad thing. We can easily retrofit it, and the ECM technology is one really nice way to exceed our ASHRAE 90.1 requirements. So it gives us a much easier path towards getting there. Just some final thoughts, and then we have plenty of time for questions. We'll be online just as long as you need us and as long as there are more questions. But a lot of applications available today. Let's take advantage of the latest technology, which would be variable speed pumping, so we meet all the requirements. But we also have to look at system type. So we want to consider a cost-effective system based upon operating costs. That's, of course, important. We're picking a very efficient heat pump. So we want to look at the total system cost. Whether it's a single speed or two-stage heat pump, that has a bearing in how we design the system, because we want to take advantage of that part load operation with even lower flow rate. Lowest pressure drop is the smallest pump. So we want to always look at pressure drop. And then system type, we might want to consider primary, secondary with hydraulic separator to keep the pump sizing lower. But then once we have that decision made, component optimization is a pretty big deal. We can do a lot with just picking the right zone valves. A CV that's higher gives us a lower pressure drop. We want to have hydraulic separators to help with the pressure drop. Expansion tanks are going to keep our system from having a problem with low pressure. So that's also important in all this coming together as one efficient package. All right, so we have plenty of time for questions. See, we have a number of people on the line here. I'll just hold off here till we have all the questions answered. Thank you again for your attendance. I think I have a slide here that has the Intertech contact information. Oops, I'm sorry. I guess that was the beginning of the slideshow. So make sure you contact Intertech if they can be of any help in designing the system. But there's also a lot of technology that can be helpful here. Here's Intertech's number, 618-664-9010 for their inside sales team. So again, we'll hold off till we have any questions. Thank you again.
Yeah, thanks again, Jeff. Fantastic job. I think that was a great overview of commercial pumping and efficiencies and system design. And we'll see if we have any questions here. And if we don't, again, thanks a lot. Thanks everybody for joining us this morning. And we'll continue to bring these webinars to you, and hopefully you continue to join us, and we can help just further your education on geothermal heat pump systems. Well, I don't actually see any questions here. Just a nice comment that enjoyed the webinar. So I think with that, Jeff, we'll go ahead and end the webinar, and thanks again. I appreciate your time.
All right, thank you, and thank you everybody for joining us.